Hello and Namaste. In continuation of the partial differentiation topic, composite function will be going ahead with the part 1. We have divided the part in different parts of this composite function depending upon the scenario, how the function, one function dependent variable is depending upon the other, and then those other variables are depending upon the other variables. So this is about the composite function part 1. So now change in independent variable x and y in another variable t. So let us suppose differentiation of a composite function, let z equals to f of x comma y, where x is a function of t, y is also a function of t. Then z is called the composite function of t. Now how this particular graph would look like, or a tree diagram would look like, if you wanted to draw this 3, 1, 2 and 3 type of functions in a graph, it is nothing but z equals to f. This which is depending, this z equals to f is depending upon the functions x and y, but this x and y depending upon the variable t. So this z equals to f is the variable in the level 1. X and y, these are the variables in the level 2, and t is the variable in level 3. If we'll draw in this way, I call this as a tree diagram. There is no such word, but this I call it as a tree diagram because it is giving you the feel of a branch of a tree. So in this way, suppose we wanted to differentiate this z with respect to t. Now this z is a variable which is placed in level 1. T is this variable placed in level 3. Now if you'll observe here in the level 3, we have got only one variable placed. That means if we wanted to differentiate z with respect to t, it would be dz upon dt. And then whenever because it's a level 2 is also there in between or in intermediate level, we have to take care of these variables also, because z is not directly depending upon t. Z is depending upon t via this functions x and y. So this is we have to take care of, and this is known as a chain rule for the composite function or a differentiation. So this dz upon dt is equals to dou z upon dou x. Why this is dou z upon dou x? That means this z is depending upon the level 2 variable x and y, and we have got in the level 2 we have got two variables, that is more than one variable. That's the reason this is coming out to be dou z upon dou x into dx upon dt, because this x is a level 2 variable and t is a level 3 variable. Again this x is depending upon only one variable. Similarly, y is also depending upon only one variable. So we have to have this as dx upon dt. Similarly, dou z upon dou y into dy upon dt. The same thing will happen here. And this dz upon dt is called total differential coefficient of z. Let us see this using one example. If u is equals to x cube plus y cube, where x is equals to a cos of t and y is equals to b sin of t, then find du upon dt and verify the result. So now what this type of figure, again the same type of figure will happen, because u is a function. So instead of this z we have got u here. So u is a function of x and y, but x is a function of t, y is also a function of t. So this type of function will look like something like this here, and therefore this is what we have seen in the last slide. Instead of z we are replacing it with u. So du upon dt is dou u upon dou x into dx upon dt plus dou u upon dou y into dy upon dt. Therefore dou u upon dou x, that is differentiation of u with respect to x, will gives us 3x square, and this dx upon dt, that is differentiation of x with respect to t, will gives us minus a sin of t. Similarly, dou u upon dou y as 3y square and dy upon dt as b times cos of t, because this a and b, they are the constants, so only cos of t and sin of t differentiation will happen here. And therefore this, after simplification further, will be getting something like this here, that is minus 3a cube cos square t sin t plus this b 3 times b cube sin square t cos of t. Now what this how this cos square t has come here, because we are differentiating u with respect to t, so we are trying to bring every variable in terms of only t. That means what, we have to replace this x and we have to replace this y using this x is equals to a cos of t and y is equals to b sin of t. That is what we have done it here, and this becomes, so we have just substituted the value of x and y here. So this is what we got it as du upon dt, which is completely in terms of t. We do not have any x and y in between. Now what would be the verification of this type of result? We have to do it, that is u is equals to x cube plus y cube. So we have to find out this is nothing but x, we are replacing it as a cos of t, y is replacing as b sin of t, and then we have to just do the complete differentiation of u with respect to t. That would give us with respect to, so that is nothing but minus 3a cube cos square t sin t plus 3b cube sin square t cos of t. This is just a simple complete differentiation of the u with respect to t without doing this type of chain rule in between. If you are directly substituting u or converting this u with respect to t only, and then we are differentiating it, we are going to get this type of this. And if you'll observe here, this and this will gives us the verification of this particular theorem. Okay, and this is one of my favorite, which is a self-observation. If z is u square plus v square, u is a function of at square, v is a function of 2at, find dz upon dt. Similarly, if z is sine inverse of x minus y, x is 3t, y is 4t cube, show that this type of question or self-observation slide will give you the practice session, whatever the concept we have just done so far. I hope you are getting this type of examples. I'm trying to reduce the speed of the reduce the length of the video so that you will get the concept fast. Okay, thank you so much. Happy learning.